Hello and welcome. My name is Carol Weiss from Remote Energy, and today we will be talking about the effects of temperature and irradiance on our solar module PV production. Here are the learning objectives. By the end of this presentation, students should be able to do the following. Number one, you should be able to explain how changes in temperature and irradiance affect the IV curve of a PV module. And said a different way is you should be able to explain if it's a hot day or a cold day, or if it's a very sunny day or it's a not very sunny day, how is that going to change the electrical characteristics of our PV module? How will that affect our voltage, our amperage, and the power production of our PV module? The second learning objective, you should be able to discuss the tools and techniques for measuring the temperature of the solar module cells and solar irradiance. So this is very practical. If you go out to a job site and you're trying to determine if a PV module or a PV array is working well, you can measure their volts and their amps, but if they're not exactly the same as the module spec sheet, you should be able to measure temperature of the cell and say, oh, I think my voltage isn't reading the same as the spec sheet because of the temperature change. Or maybe it's late in the day when you go there, so you don't have as intensive sun, and so that may affect your current. And so you need to have the tools and know how to measure that to see how those conditions will affect your PV module performance. And then the last one is, by the end of this presentation, you should be able to calculate an estimate of the PV output current for different measured irradiance conditions. So there's a tool we can use to measure the sunlight intensity of that day, and we will be able to calculate how much current we think the module should be producing in that condition. Let's start by looking at a module spec sheet or specification sheet. So we can find out the electrical parameters of a module either by looking at the backside of a module at the nameplate rating, or if we want to get more information, we would look at the module specification sheet from the manufacturers, which could be found on their website. So for this module, this is a SolarTech module, and they're giving us the electrical characteristics of this module. And every single module has to be, by every single manufacturer, has to be tested at the lab at certain standard test conditions. So it has to be tested at a certain temperature and at a certain light intensity, and so that they can be compared one to another. And then they come up with these electrical characteristics that they put on the nameplate on the backside of the module and on their specification sheet. So this module is telling us that it can produce its maximum power it can produce at those test conditions is 110 watts. Then they tell us the maximum power voltage and the maximum power current. So it's called VMP for short and IMP for short. And so we have 17 volts that it can produce at maximum power, and 6.5 amps is how much current it can produce at maximum power. And since volts times amps equals watts, if you took your calculator and you multiplied 17 volts times 6.5 amps, you'll see that you'll get around 110 watts. So that's when the circuit is running under load, this module will produce about 110 watts with this many volts and amps. They also give us two other readings. One is the short circuit current, and here current is, the acronym is I for intensity, so it's ISC for short circuit current. They're saying that that is 7.1 amps, and that would be if there was a direct short. So this is kind of the maximum amount of current that you could ever see. It's not typically, you're not going to typically see this under load. This would be under a short circuit condition. But we use this conservative number when we do wire sizing. So that would be discussed in a different presentation. And then we also see that they have the open circuit voltage, or VOC, open circuit voltage. And this again is an extreme number. This is if the PV array was not connected to anything, there was an open circuit. This would be a maximum amount of volts that we would see. So it's 21.4 volts. It's higher than the voltage that we would see if we were running the circuit on or under load. These are the main electrical characteristics that we're going to talk about in this presentation. Briefly, there's other information here on the spec sheet, including the module efficiency, the power tolerance. They're telling us that this is a nominal voltage 12-volt module, which means that we could connect this into a 12-volt system. A single module could be charging a 12-volt battery, so we would be at a slightly higher voltage, 17 volts to start, and then we would be charging a 12-volt battery so that we would push the electrons to the battery. It's giving us temperature coefficient, so it's telling us, we're not going to quite get too detailed into this in this presentation, but this is how it's telling us how our electrical parameters or characteristics are going to react with changing temperatures. And so that's how, there are different numbers for the VOC, for the power, or for the short circuit current. And then we're really not going to be talking about the rest of this for this presentation, but the spec sheets always give you a lot of information. Standard test conditions are the conditions in which module manufacturer labs have to fix at their laboratory so that they can test their modules under the certain conditions and obtain their electrical characteristics. We have to have fixed conditions so that we can compare different modules to each other. So if this manufacturer A, they have to fix their conditions to the same conditions as manufacturer B, so that when they both label their modules, we know that they were tested under the same conditions. And so we're going to look at what conditions they use. First, they have to fix the sunlight intensity, because if it's a bright sunny day, the modules are going to produce more current and they're going to produce more power. And so every manufacturer has to test to the same sunlight intensity. And so they fix it at 1,000 watts per meter squared. So that means 1,000 watts of sunlight intensity on a square meter. This would be like a bright sunny day almost anywhere in the world. And so they're trying to create a nice sunny day in order to see how this module will work. The second characteristic or condition that they create is they have to fix the temperature. And when they're fixing the temperature, they're not talking about the ambient temperature in the room. They're talking about the cell temperature. So if you're touching the cell, how hot is that solar cell? So they're fixing that at 25 degrees C cell temperature. Okay, so all module manufacturers fix these conditions in the lab, they flash test them, and then they are able to obtain the maximum power of that module, the maximum power voltage, the maximum power amperage, the short circuit current, and the open circuit voltage. And then they create that label that goes on the back of the module. These are the two most important standard test conditions from a technician's point of view, because these things change throughout the day and throughout seasons. And so if you are, as a technician, go up to a PV array at the beginning of the day, let's say the sun's just coming up, you're not going to have very much sunlight intensity. And so therefore, that solar module is going to be performing different than in the middle of the day when we have a really bright sunny day. It's going to be actually producing more power in the middle of the day. And then our temperature, of course, is changing all the time as well. So even if in that same example at the beginning of the day, we probably have cooler temperatures. And so our module is going to be performing in a certain way versus in the middle of the day when the sun is hitting it and it may be heating up. So we have to really, these parameters are making our module perform differently all day long, and then it changes, per season, especially for locations that have extreme weather changes. There is a third standard test condition that the labs need to set up, and that is it's also measured at 1.5 Earth atmospheres, and that just means where the sun is in location to the PV array and at what angle, how many atmospheres you're going through. But since this is nothing that we can change as an installer and it doesn't change for us throughout the day and throughout the seasons, we do not talk about that very much in this class. So that's the only place you're going to see that standard test condition. But these are the three things that are fixed at the lab and in which the module manufacturers obtain the electrical characteristics. This is a module IV curve. IV stands for, the I stands for amps or intensity. So it is this vertical axis here on this graph. So we're plotting current of a module, and we're plotting the voltage. The V stands for voltage. So an IV curve is made for every single module when the manufacturer tests that module at standard test conditions. So for this IV curve, we're going to look at the module that we were using 2 slides ago. So remember that module had 110 watts, okay? When they apply the standard test conditions, 1,000 watts per meter squared of sunlight intensity, 25 degrees C, cell temperature, to this module in the lab, they plot out the IV curve here, which is the yellow line. And then the blue line is the power curve. And this is how this module will work under those test conditions. And this is how they can derive the electrical characteristics to put on the nameplate of the module and on the specification sheet. So at 0 volts, when there is a direct short circuit on the module, this module will produce 7.1 amps in short circuit condition. Okay, when there's 0 amps, this module, and we have an open circuit, so our system is off, the maximum amount of voltage that we will receive under standard test conditions is 21.4 volts. And then they look at where on this curve do they get the most amount of power, because everything that's underneath inside of this yellow line is watts. It's power, because power is amps times volts. Okay, and so they're looking for at what point do we get the most amount of power, and where the star is, that's the maximum power point. And so we bring that across to the amperage, and the IMP is 6.5. So they put that onto the nameplate, and we come down here to the volts, and we have the VMP is 17.0 volts. And when we multiply those two together, we get 110.5 watts. And so that is how they label that module 110 watts. Okay? So the module IV curve is really just showing us how this module works under these set conditions. And why we're going to review this is because now we can look at what happens to this IV curve if we have hotter conditions or colder conditions, or we have more or less sun. What will happen to this IV curve? And it helps explain how a PV module works. Next, we are going to look at an IV curve and notice what happens to the voltage and how it changes with changing temperature. So here we have an IV curve. We don't have any of the values associated to it, but this is what it looks like. So remember that the current is going up the vertical axis and the voltage is on the horizontal axis. And so we're saying that under normal standard test conditions at 25 degrees C cell temperature, this is what the IV curve looks like. Now, if we have colder temperatures, so instead of 25 degrees C cell temperature, now we're at 0 degrees C. What happens to our voltage is that the voltage increases, okay? And the amperage really stays close to the same. It drops a little bit, but the most significant thing that happens is that our voltage increases. And therefore, this, the maximum power point, or the amount of power that we get out of that module, increases as well. So colder temperatures can produce more voltage and more power. The next condition is that if we have hotter temperatures, so on this red line now is 50 degrees C. And remember, this is not ambient temperature. This is cell temperature. So if your module is on a roof, it's in direct sunlight, it's a dark color module, your roof is hot, there's not much airflow, it's very easy to get to these temperatures, even if you're in a cooler climate. As our cell temperature increases, what happens to our voltage is it decreases. Okay, so it's inverse, there's an inverse relationship. So we increase the temperature, it reduces our voltage, and therefore, remember our power point is right here, so the power is going to decrease as well. So in that case, with the hotter temperatures for this red line, it increases the current slightly, but it's not very significant. So the biggest thing when we think about temperature, we think temperature affects voltage, and because volts times amps equals power or watts, then it's also going to affect our power. So increasing temperature not only reduces our voltage, but it's going to reduce our power. That's the big take home on that slide. One of the ways that we can test the temperature is with an infrared temperature device or a temperature gun. And how we use this is typically we're using this infrared temperature sensor on the back side of our module. So our module would actually be facing the sun. It probably would already be mounted perhaps on, let's say this is a pole mount, and we wanted to see how hot the module was getting. We would put the infrared temperature gun on the back side of the module. If you test on the front side of the module, a lot of times you will get reflection, and so we won't get a true reading. So it's best to test on the back side of the module. We point it 90 degrees perpendicular to the back of the module. There's many different types that are out there, and so you have to read the directions as to how far you need to be away from it, and you can test the temperature. And why we would do that is if we wanted to see, if let's say we went out and we were troubleshooting a system, somebody was saying that they didn't think that the PV array was producing as much as they thought that it should, and we went out, we saw that the voltage was low, we actually could test the temperature and we could do calculations to see if it was reading correctly according to the manufacturer specs. So this is just showing, again, that it's incorrect to test on the front side of a module, and we also need to be 90 degrees perpendicular to the back side of the module, not at an angle, and we don't want to test too far away from the back side. We can apply the temperature changes that we see out in the field directly to a module by looking at its specification sheet. Each specification sheet is going to have temperature coefficients written on it. And so here we're seeing that there's temperature coefficients for the open circuit voltage, there's a temperature coefficient for the maximum power, and there's a temperature coefficient for the short circuit current. And they each have different values. Looking at the first value, we can see that for each degree C of temperature gain that we have, that the voltage will change by a negative 0.36%. So negative means that the voltage is going to drop. So the hotter the day that we have, our voltage is going to drop, which is what we saw on the IV curves earlier. Then when we look at the temperature coefficient of current, we're going to notice that for each degree C temperature gain that we have, the current changes by a positive 0.05%. This is a very small amount of current gain, so we typically do not talk about that hotter temperatures we get current gain because it's only a 0.05% gain. So it's pretty negligible when compared to the voltage decreases that we're seeing. And then when we look at the power differences for every degree C temperature gain that we have, our power is going to change by a negative 0.46%. So we can take the real calculations that we see out in the field and we can apply it to the specific module that we're using by looking at its specification sheet. And notice that these temperature changes were written in percent per degree Kelvin. And we have a note here that says 1 degree K is equivalent to 1 degree C. So that is just the side note for looking at temperature changes. Next, we are going to look at how current changes with irradiance. So we are showing a lot of IV curves here, and we're going to start with the one that's 1,000 watts per meter squared. So current is really the big factor that changes when irradiance changes or sunlight intensity changes. So 1,000 watts per meter squared would be a bright sunny day. If we see more than 1,000 watts per meter squared, such as up in the mountains, we might see more, or if we have snow reflection in the area that we're in, we may see more than 1,000 watts per meter squared. So here we had our short circuit current was 10 amps. When we go to 1,200 watts per meter squared, it's going to be closer to 12 amps. If we decrease the sunlight intensity or the irradiance down to 800 watts per meter squared, we now see the short circuit current at 8 amps. If we go down to 600 watts per meter squared, we see 6 amps. So we're seeing a relationship here that the current increases proportionally with irradiance. Okay? Let's look at the other characteristics. So we see that current is really affected by irradiance. Let's look at power next. Since power, the equation for power is amps times volts, if we're seeing an increase in amps, we're also going to see an increase in power. So as the sunlight increases, we're going to have more power coming off of our modules. And we're going to see that the voltage changes a little bit with the changing irradiance, but it's very slight. So we don't consider it a big factor when we're doing when we're going out and troubleshooting and seeing how our system is operating. So the big take home here is that as the irradiance increases, our current and power is going to increase as well. We can test irradiance with a tool called a paranometer. Okay? So one form of a paranometer is one that looks like this, and there's a reference cell, solar cell at the top that we want to face in the same angle as our module. And then this is the meter readout, and it will tell us how many watts per meter squared it is seeing at a particular angle. So when we are using that to test how many watts per meter squared our module is seeing at a certain time, we actually need this reference cell at the top of our paranometer to be at the same angle and plane as this module. Okay, so then if it's at the same angle and orientation and the same plane as this module, then it will be seeing the exact amount of watts per meter squared as our module is. So notice that we have it flat here, so it's not creating any shadows on our module. Here are some incorrect ways of doing it. So here we have the paranometer up really high. Here we have it on top of our module and it's creating shade. Here the reference cell is facing downward, so it's not going to see the same amount of watts per meter squared. So that's how you would use a paranometer. Next, we will apply the irradiance changes that we see with our paranometer. So the scenario is that we're out on a job site, the system's running, we know what the module nameplate rating is. So we know that the module says that it will give 6.5 amps. We found that on the module spec sheets if we're at 1,000 watts per meter squared. So if we're under ideal standard test conditions. But we took our paranometer, we put it at the top of our module at the same tilt angle and orientation, and it reads 894 watts per meter squared. So we know that since this number is less than 1,000 watts per meter squared and current is proportional to irradiance, that we should be seeing less than 6.5 amps. We're only going to see 6.5 amps if there's 1,000 watts per meter squared. If we have less than 1,000 watts per meter squared, we will see less current. Okay, that's the general rule. It's proportional. So we can actually do math and figure out exactly how much current we should be seeing based on this. And so we're taking the measured irradiance and we're dividing it by the 1,000 watts per meter squared, which is the standard test condition irradiance. And then we multiply that by what we should have been seeing of our current, which is 6.5 amps. And this is telling us that when we go out and measure what we are seeing under these conditions, these specific conditions, we should only be seeing 5.8 amps. So on our last slide, we just want to look at the effects of irradiance one more time, where we're saying that if the standard test conditions state that the IMP is 6.5 amps at 1,000 watts per meter squared, then if we have a sunnier day, we should see more amps, correct? And so the mathematical equation is that we would take 6.5 amps, we'd multiply that by this ratio, we'd put 1,200 watts per meter squared over 1,000 watts per meter squared, and when we do that math out, it's 7.8 amps. So the more intense of a sunny day it is, the more amps we're going to see from our solar module. The opposite is true. If we only have 600 watts per meter squared, the question is, what is the IMP at 600 watts per meter squared? Or what is our maximum power current at 600 watts per meter squared when we have some clouds or it's later in the day? So we do the same math. We take the 6.5 amps, we multiply it by the ratio. We put 600 watts per meter squared. We divide that by 1,000 watts per meter squared, and that equation comes out to 3.9 amps. And so the cloudier the day is, or the less sun that we have, the less current we have. And then finally, if we really don't have we have very little sun, we only have 200 watts per meter squared, we're going to have very little current, 1.3 amps, by doing that same equation. So if the equations are difficult for you, I suggest looking at this last slide a little bit more and make sure that you're familiar with this. And intuitively, this makes sense. We kind of feel this on our skin. If it's a bright sunny day, it's intense. And so it's kind of an intuitive way to think that there's going to be more current. Okay, and if it's a less sunny day, there's going to be less current. That concludes this PowerPoint presentation. Thank you very much, and we look forward to seeing you in further presentations.